Here we are going to discuss finite differences and the finite difference formulas. Finite differences, just a mathematical technique that we employ to approximate derivatives of a given function at the point of interest. Call it x naught, any other point. Then the finite differences are into three, that is the forward difference, backward difference, and the central difference. For a forward difference, you approximate the derivative at that point of interest and the point ahead by h, or the difference, I mean the small change from the initial point and that point ahead. Then, of course, our goal is just to approximate the first derivative, and from the first derivative approximated, you can approximate many other derivatives. So here we use Taylor series for this one, because this one is indeed that one. So when I use Taylor series, I will expand f of x plus h, and of course I will obtain this one in that order. Now, when I still go back to the forward difference formula and put in what I've expanded from the Taylor series, I'll get that. Then, of course, I won't forget that there is a subtraction here minus f of x. When I open brackets, of course, this will cancel and end up with this. Approximating the first derivative, what do? It's like we just have to call that. When I divide through by h on both sides, here, when I divide through by h here, of course, I'll just remain with delta f of x out of h, but here I'm going to put approximation signs to the first derivative of x, y. Because other terms is like they are just truncated off y. The reason is just because the error becomes too small as it goes on for higher order powers. Okay? So that's why we shall just approximate it to be just this, but of course in actual sense, other terms still prevail with more higher orders. Then that was for the forward, and you do all these forward, backward, and central. They have a common thing, that is you should have x values equally spaced. So here we are considering the function f of x for equally spaced values of x. First was forward differences, so this is backward difference. Backward differences has nothing different than just because you're taking something behind. So we shall use the number operator, which means you're approximating the derivative of the function f of x at a point behind or even below the point of interest by h units. That's why having a negative h here. So, of course, this one is just f of x. When I apply Taylor series expansions on this is what I will attain. And upon that, putting it back into this formula for the number f of x, I'll actually get this. And as I open brackets, this f and this f will cancel out because this is subtraction. And of course, I remain with this negative into the whole of this. So it will be negative, that's a positive, h, and so many other terms. Of course, for all these finite differences, we aim at approximating the first derivatives upon which you can build to derive other derivatives. So this is the approximation for the first derivative from all we use as Taylor series. Likewise, for the central difference, the only difference for the central difference is just because you aim at the center. Suppose you have the point x naught, the point behind and the point ahead is just going to differ by just h by 2. Since all of them are just a height or a width of h by 2 altogether. Such that when you add h over 2, this will come back to h, which is the original width or interval. So basically this is it, having operator that one. And when we try to go on and use Taylor series for each case as this and this one, we shall attain this one. And of course lastly we end up with this one. This we can use it to make a builder for the central approximation and finally approximate the first derivative. Thank you for listening. Good afternoon, Teacher Mas.
I'm going to discuss about the central difference operator, which is denoted by delta this one, and it is defined as delta f of x equaling f of x plus h over 2 minus f of x minus h over 2, which is the difference between the function y at the point ahead of it and the point behind it by h over 2. The following are the properties for linearity. For the function, for the central difference operator to be linear, it should satisfy this property. Now, from this one, from here, I will put this delta to both this function and this one, and I get this one. Then when you continue and expand this one, you end up getting this one. So there is another one, scaling property, which is delta f of ax equal to, when you expand this one, you put out this constant outside, then you remain with a delta f of x. Then when you continue to expand this one, you end up with this function. Then another one is the translation invariance, which is the central difference operator is translation invariant when it satisfies this property from delta f of x plus c. Here you neglect or remove the constant and you get the delta f of x, and when you continue and you expand this one, you end up getting this one. And these are the properties of the central difference operator. Then after, we have the assumptions of the central difference operator. The first one is smoothness. And I think for central difference operator, they are we continue with the assumptions of the central difference operator, where we have smoothness, differentiability, small scale. For the function to be smooth, it should be continuous. And for the case of differentiation, for the function to be differentiable, it should be well defined. It should be well defined. It should have well defined derivatives at all x values, and it should have a small width. Then, for applications of the central difference operator, I think we can apply it in physics or engineering when you're determining the partial derivative of function. As I conclude, the central difference operator is the most accurate method. It's the most accurate method compared to forward and backward methods.
Thank you.
Thank you.
Yes, hello, good afternoon.
Good afternoon.
I'm going to be talking of the shift operator. So a shift operator is the kind of operator that shifts a function by a certain amount, or it shifts the argument of a function by a certain amount. So we have two kinds primarily of an operator, a shift operator. We have the backward operator, backward, and then we also have the forward operator. For the backward operator, it shifts the argument of a function by one more unit forward or in front. Then the backward operator shifts the argument of a function backward by again 1 unit. So what does it literally mean? We can have an example of a forward operator. And say if we have, by the way, shift operator is denoted by E. So you have a shift operator of a function f of x. Can have that. If you have it like, if it is equal to you can assume that if f of x, so if we have f of x being equal to x squared, and you have the shift operator of f of x will be equal to f of x, we shall have x plus h but squared. This is the first operator of, this is an example of an operator of the first difference operator. Then the second one, we shall have for the forward operator, it will be equal to x plus 2h. We can see that this one is shifting by 2 units and this one is shifting by 1 unit, and it is squared. Then for applications to daily life, we can relate this to one like video processing or photo video processing or taking a photo. When somebody zooms in and out, that person may be increasing the magnification by a certain amount or reducing it by a certain amount. Then we can also have a vivid example on the calculator, how we calculate these things of decimal points, how we round off. We can round off 1.449 to 1.5. So this is a backward operator that we are shifting this forward by some other decimal point, which is 0.1. Then we can also have 1.4403 being shifted to 1.4. Then we are reducing it by a certain amount. Otherwise, I would like to submit. Thank you so much.
Okay, good afternoon, teachers.
Good afternoon.
I'm just going to discuss about the relationship between the forward difference operator, a backward difference operator, the shift operator, a central operator, and the mean. Then, first of all, for the interest of time, I'm just going to talk about the relationship between the forward and the shift, then a backward and the forward, the backward and the shift. Then we talk about the average and the shift. So we are just going to see how these things are related. We are just going to see how these operators are related together. First of all, we are going to first deal with the relationship between the forward operator, which is denoted as this one, and the shift operator, which is denoted as this one. So we all know that the forward operator is given by this formula here, f of x plus h, whereby h will always stand for the interval between the x values, and then f of x. But we all know from here, the shift of f of x is equal to f into x plus h. So we are now going to feed in this one into this equation here. Then, after feeding in that, we shall get, or we shall come into this one here. So we are now going to feed this one into this. So this is the step. Then from there, we got this step here. The forward operator, which is equal to E of O. Okay, E of f of x minus f of x. From here we factor out f of x. Then here we have factorized out. We remain with this one in brackets. Then after all, we divide both sides by f of x. So that means the relationship between the forward operator and the shift operator is E minus 1. This is the relationship between the forward and the shift operator. Then from there, we are just going to see the relationship between the backward and the shift. We all know that the backward is given like this. It's called f of x minus f of x minus h. But then still, we know that the shift is given by f of x plus h. But then when we see here, we have a negative and we have a positive here, meaning we have something like the inverse. Together, we shall have this one here, shall stand for f of x. Then this one will be, it's got f of x minus e inverse From here, we can factor out f of x into 1 minus. Then I'm over. Then we divide through by f of x. To get 1 minus.
Hi, good afternoon.
We are going to talk about neutron divided differences. Now, under neutron divided differences, we are seeing that it is used to generate interpolating polynomials where we have discrete data points. As well, we can use it in the numerical analysis to estimate the polynomial function where we give a data points. As well, our neutron divided difference, it is given by this formula where we have our polynomial, which is of our
Degree
polynomial
n.
of degree n, but it is a function of a x. We have n naught, a1, x minus x naught, and we proceed. But we are seeing that this one, it is less compared to this one because we are finding differences between intervals. Until we can value which we don't know, which is a x minus x naught dash dash x minus xn, but what is the meaning of n naught and x minus x naught? We are going to find that our a naught is this, is that divided, is their zero, is that zero divided difference, which is n naught is equivalent to x naught from where we get our function of x naught, which equals to x naught. We go to the first divided difference. First divided difference we are going to find when our n equals to 1. X from x naught to x1, which is equivalent to f of x1 minus f of x naught. Similarly, we divide it with x1 minus x naught. Second divided difference, we are just seeing an increment from x naught, x1 up to x3, which is equal to function of x1 and x2. The bigger, we subtract the one which is smaller because we are under forward differences, which is x2 minus x1. Let's consider when n divided difference, where we have x1, x naught, x1, x2, up to xn minus 1, which is less. Of course, the bigger will be xn, which is equivalent to our f of x, which is x1, x2 minus xn. We subtract our function, which is less, x naught, x1 minus xn minus 1, which equals under all of it under xn minus xn.